To begin the lesson, let's consider the function p of x equals x cubed minus 11x minus 20. We are asked to divide p of x by x minus 4. So let's do a synthetic division. The 0 of the divisor goes in the box, and then we're dividing into the dividend 1x cubed plus 0x squared minus 11x minus 20. Bring down the 1 times 4 is 4, add that column. 4 times 4 is 16, add that column. 4 times 5 is 20, and we get a remainder 0. By the remainder theorem, p of 4 must be equal to 0. Notice that that means that x minus 4 and x squared plus 4x plus 5, the result of the division, are both factors of x cubed minus 11x minus 20. In other words, whenever we have a 0 remainder, both the divisor and the quotient are factors of the dividend. So, this brings us to the factor theorem. A polynomial p of x has x minus c as its factor if and only if the value of p of c is equal to 0. In example 1, we are asked to consider the function f of x and find the value of f of negative 2. So I'm just going to find this the traditional way. F of negative 2 is negative 2 cubed plus 5 times negative 2 squared minus 4 times negative 2 minus 20, which is negative 8 plus, and then the second term is 5 times negative 2 squared. Negative 2 squared is 4 times 5 is 20, and then the third term is negative 4 times negative 2, which is positive 8. And you'll notice that we have a series of terms that are their opposites. Negative 8 and 8 add up to 0, 20 and negative 20 add up to 0. So f of negative 2 is equal to 0. What does this result imply? It implies that x plus 2, which is would be the divisor, is a factor of f of x. So let's use our synthetic division now to write this in partially factored form. So we're going to divide by x plus 2, and we're going to divide into f of x equals 1x cubed plus 5x squared minus 4x minus 20. And we are expecting a remainder 0. So bring down the 1 times negative 2 is negative 2. Add that column, that's 3, times negative 2 is negative 6. Add that column, that's negative 10, times negative 2 is positive 20, and we do get a remainder 0. The result is that f of x factors into the divisor, x plus 2, times the quotient, x squared plus 3x minus 10. So there's a partially factored form. Now we're going to write f of x in fully factored form and find all of its zeros. So f of x equals x plus 2, our first factor, plus, times, and then let's take x squared plus 3x minus 10 and factor it further. That factors into x plus 5 times x minus 2. And so when we're asked to find its zeros, we can also say find its roots. That is, find the solutions to the equation where f of x is equal to 0. So that would be where x plus 2 is equal to 0, or where x plus 5 is equal to 0, or when x minus 2 is equal to 0. So its zeros are negative 2, negative 5, and positive 2. Let's consider another function in example 2, g of x equals x to the 5th minus 2x to the 4th plus 3x squared plus 5. We're going to find the value of g of 1, and g of 1 is 1 to the 5th minus 2 times 1 to the 4th plus 3 times 1 squared plus 5. All those powers of 1 are equal to 1, so now we have 1 minus 2 plus 3 plus 5, which is equal to 8 minus 2 is 6, plus 1 is 7. And since we did not get 0, x minus 1 is not a factor of g of x. And I'm just going to write my reason here, because g of 1 is not equal to 0. All right. And furthermore, is x minus 1 a solution to x to the 5th plus 2x to the 4th plus 3x squared plus 5 is equal to 0? And that would be no, again, because g of 1 is not equal to 0. All right, let's take a look at example 3 and determine if x plus 3 is a factor of each of the following functions. So if we want to know if x plus 3 is a factor, we can test it by finding h of negative 3. h of negative 3 is negative 3 cubed plus 2 times negative 3 squared minus negative 3 minus 6. That would be negative 27 plus, and negative 3 squared is 9 times 2 is 18, then plus 3 minus 6. And so that would be negative 27 plus 18 is negative 9, plus 3 is 12, minus 6 is 6. So since h of negative 3 is not equal to 0, no, x plus 3 is not a factor. And now let's do the same for b. Again, we're going to find p of negative 3. p of negative 3 is negative 3 cubed plus 7 times negative 3 squared plus 17 times negative 3 plus 15. That's negative 27 plus 9 times 7, which is 63, plus 17 times negative 3, which is negative 51, plus 15. That does give a value of 0, so the answer there is yes, x plus 3 is a factor. All right, in example 4, we're going to determine if 6 is a solution to the following equations, and we can do that by substituting, but we can also do it by synthetic division. So let's use synthetic division. We're dividing by x minus 6, because if x minus 6 is a factor, then 6 is a solution to the function equal to 0, or it's a 0 of the polynomial. So using synthetic division, 2 times 6 is 12, add that column, that's 1, times 6 is 6, add that column, that's 1, times 6 is 6, and we do get a remainder 0, and so yes, 6 is the solution. All right, let's test in b using synthetic division. So we're going to divide the polynomial here by x minus 6 and see if we get a remainder of 0. Bring down that 5 times 6 is 30. Add that column, that's 7 times 6 is 42. Add that column, that's 2 times 6 is 12. And this time we get a remainder of 6, so no, this 6 is not a solution in this case. In example 5, we're asked to verify that negative 1 is a solution to this polynomial equation, and then find the complete solution set. The best way to do this is to assume that x plus 1 is a factor and divide. So divide the polynomial by x plus 1, and the 0 of the divisor goes in the box for synthetic division. Bring down that 1 times negative 1 is negative 1. Add that column, times negative 1 is 7, and add that column, and then times negative 1 is negative 10, and we do get a 0 remainder. So that means that not only is x plus 1 a divisor, or a factor that we already knew, but the other factor is x squared minus 7x plus 10. So if we set that factor equal to 0, we'll find the other two solutions. And it just so happens that this trinomial factors into x minus 2 times x minus 5. So that means that x minus 2 is equal to 0, or x minus 5 is equal to 0. And that means that x is equal to 2, or x is equal to 5. That means our complete solution set is all three solutions, negative 1, 2, and 5. Pause the video while you try the next one on your own. And there's the complete solution set. Be careful with your synthetic division. A really common place to make an error here is to forget that there must be a zero placeholder for the x squared term in the dividend. All right, this brings us to the fundamental theorem of algebra. If the polynomial p of x has an nth degree, then p of x has exactly n roots. Now, what do we mean by roots? Roots are solutions to the equation p of x equals 0, and the degree of a polynomial function is equal to the highest exponent of x in the equation. So, in example 6, for instance, if we have a polynomial f of x equals x cubed plus 8, and we are asked to find all roots, the roots are solutions to the equation f of x equals 0. So since it's a third degree equation, the highest exponent on x in this polynomial is 3, so that means that there are going to be 3 solutions. We're going to guess the first one. Now I'm going to guess that x equals negative 2 is a solution, and I'm going to verify that by negative 2 cubed plus 8 is equal to 0, which means that negative 8 plus 8 is equal to 0. That is a check on that solution. So if I realize that that's the first solution, I can divide to find other factors. X plus 2 must be a factor, so I'll divide by x plus 2. And we're dividing into 1x cubed plus 0x squared plus 0x plus 8. And then bring down the 1 times negative 2 is negative 2. And add that column times negative 2 is 4. Add that column times negative 2 is negative 8. And we do get a 0 remainder. That means that the other factor, which I'm going to set equal to 0, is x squared minus 2x plus 4. Now, this is a great one for the complete the square method, so I'm going to add a blank and add negative 4 to the other side of the equation. Let's make a picture of the complete the square. So I'm going to zoom in on this a little bit. And if we make a picture for complete the square, x squared is the first term. Divide the middle term into 2 equal pieces, negative 1x and negative 1x. That suggests that we have factors of x minus 1 and x minus 1. Negative 1 times negative 1 equals positive 1 completes the square. So this trinomial turns into x minus 1 squared, or is equal to x minus 1 squared, and negative 4 plus 1 is negative 3. If a square is equal to a negative number, that means that the expression being squared is an imaginary number. Simplifying the square root of negative 3, we get I times the square root of 3. And then adding 1, we get 1 plus or minus I times the square root of 3. So there are 3 solutions, and so those are the remaining 2 solutions. One of those solutions we already guessed, and the remaining 2 non-real solutions can be found using synthetic division and using solution to a quadratic equation. In example 7, we have a 4th degree polynomial equation, which means there will be 4 solutions. This time we're given 2 of those solutions. If x equals 3 is a solution, then x minus 3 is a factor, so I'm going to divide by x minus 3 first. And it doesn't matter what order we divide in. So let's divide by x minus 3. 1 times 3 is 3. Add that column, that's 0. 0 times 3 is 0. Add that column, that's 1. 1 times 3 is 3, add that column, we get 10. 10 times 3 is 30, and add that column, and we get 0. So remember that this is the remaining factor without its variable factors in each term. So 1x cubed plus 0x squared plus 1x plus 10. And so what we know now, though, is that x plus 2 must be a factor of it, because x equals negative 2 is a solution. So I'm going to divide by x plus 2. Bring down that 1 times negative 2 is negative 2. Add that column. Times negative 2 is 4. Add that column. Times negative 2 is negative 10. And we get our 0 remainder. So this is the remaining factor after we've divided by x minus 3 and x plus 2. So I'm going to set that factor equal to 0 to find the remaining solutions. We'll find a remaining 2 solutions here. And this time let's use the quadratic formula. X equals the opposite of b plus or minus the square root of b squared, which is 4, minus 4 times a times c, all over 2 times a. So simplifying 2 plus or minus the square root of 4 minus 20, which is negative 16, over 2, or 2 plus or minus 4i, all divided by 2. If we distribute that division, we get 1 plus or minus 2i. So now we have all 4 solutions, which are 3, negative 2, 1 plus 2i, and 1 minus 2i. 2 real and 2 non-real solutions. Alright, pause the video while you try the next one on your own. We're given 2 solutions and you're to find the complete solution set. Alright, here is the complete solution set for the try this. Now let's move on to connecting polynomial graphs and roots. Remember that roots are of a polynomial p of x are solutions to the equation p of x is equal to 0. Each real root is actually an x-intercept. Whenever y is equal to 0, that gives us an x-intercept on the graph. And if the graph of a polynomial function does not have any x-intercept, that doesn't mean that there are no roots. It means that there are no real roots, or that the roots are imaginary numbers. Let's talk about the concept of degree. So in example 8a, you'll notice that the highest exponent on x in that equation for f of x is 7. That means that the degree of this polynomial is 7, and we're expecting 7 roots to this polynomial. In b, you'll notice that the leading term is actually not, it's out of order, right? So that first term should actually be negative 4x cubed, which means that we have a degree of 3 and 3 real roots, or 3 roots. They may or may not be real. In c, for h of x, the degree of this polynomial is 5, and that means that there are 5 roots. In example 8, we'll notice that this parabola, which is a second degree function here, doesn't have any x-intercepts. That means that its roots must be imaginary. Remember, roots are the solutions to the function equal to 0. And so we can find those roots by solving that equation. And we can do that by complete the square. I'm going to draw a picture for complete the square. X squared minus 1x minus 1x gives us factors of x minus 1 and x minus 1. Negative 1 times negative 1 is positive 1, so that completes the square. And that means that x squared minus 2x plus 1 can be expressed as x minus 1 squared, and that's equal to negative 1. Taking a square root to solve, x minus 1 is equal to positive or negative I, and adding 1, the solutions are in the form 1 plus I and 1 minus I. So those are going to be my roots for p of x. In example 9, we're going to notice that this does have an x-intercept, or a 0, so negative 2 is a 0, and that means that x plus 2 is a factor of this polynomial. If x plus 2 is a factor, I can divide by x plus 2 into 1x cubed minus 2x squared minus 3x plus 10. Bring down that 1 times negative 2 is negative 2. Adding the column, that's negative 4 times negative 2 is 8. Adding that column, 5 times negative 2 is negative 10. Adding that column, that's 0. So here is the quotient for the division. We can find the non-real roots by setting that equal to 0, and complete the square is another great way to do this one. And I'm going to draw the complete the square picture here. X squared, splitting the middle term into 2 equal pieces, minus 2x and minus 2x. That suggests factors of x minus 2 and x minus 2. Negative 2 times negative 2 is positive 4, completes the square. And that means that the trinomial can be re-expressed as x minus 2 squared, and negative 5 plus 4 is negative 1. Taking a square root, x minus 2 must be positive or negative I, and so x is 2 plus or minus I. So all solutions to f of x equals 0, or all roots of this polynomial, there are 3. Negative 2 is one of them that we saw in the graph, and then 2 plus I and 2 minus I are the other 2. In example 10, you'll see a graph of a 4th degree polynomial, and we can see 2 zeros from this graph. The first 0 is negative 1, and the next one is 3. And so if I want to find the remaining zeros, I need to divide by x plus 1. And bring down that 1 times negative 1 is negative 1. Adding that column times negative 1 is positive 9. Adding that column, and then times negative 1 is negative 31. Adding that column times negative 1 is positive 39, and we get 0. And then I'm going to divide also by x minus 3, but I'm not going to divide the original polynomial. I'm just going to divide the remaining factor. Bring down that 1 times 3 is 3. Adding that column, that's negative 6. Negative 6 times 3 is negative 18. And adding that column, we get 13. 13 times 3 is 39. And adding that column, we get 0. So our remaining factor is x squared minus 6x plus 13, setting that equal to 0. And then completing the square, I'm going to put a blank on both sides and draw a picture for complete the square. We get x squared, and dividing that middle term into 2 equal pieces, minus 3x and minus 3x. That suggests factors of x minus 3 and x minus 3. Negative 3 times negative 3 is positive 9, completes the square. The trinomial can be re-expressed as x minus 3 squared, and negative 13 plus 9 is negative 4. Taking the square root, x minus 3 is positive or negative 2i, so x is 3 plus or minus 2i. And we were asked to find all 4 solutions because it's a 4th degree equation. So we have negative 1 is one of them that we saw from the graph, 3 is the second one that we saw from the graph, and then algebraically we found 3 plus 2i and 3 minus 2i as the remaining solutions.